Brendan shows up. Brendan can't, in case he can't get on. All right, let's continue on with what we were doing before. So we remember last time we were doing breaking down vectors into their components, so that you have a vector like this and it has components in both dimensions of y and x. Oh, sorry. Get this up on the screen here. Where's black? Oh. All right. So anyway, we did components of vectors, and we were able to do a problem where we added two vectors by adding their components, and that was down here at the end, which really demonstrates, that was actually on the next section, I believe, really demonstrates this idea very well. Where did it go? Where is that example? I actually don't think I had the example in the book. I think I made the example up. But anyway, we added two vectors together by adding their components together, and then creating new vector components in the x and y directions. And those new vector components were our vectors that were the components of our new vector, our resulting vector. There are other things to consider when it comes to adding vectors together and doing other simple algebraic sums, algebraic things with it, with vectors. One of these is the distribution law or distribution rule or whatever you want to call it. So you can, if you have a scalar multiplied by two vectors that are added together like this, then you can distribute that scalar to both vectors, just like you can with numbers. So scalar multiplication rather is distributive over addition and subtraction. So hold on just a second, I'll be right back. Instead of using motion control, you're just going to move the car and watch the graph of the car move. No, just use the wheels. So you're using the motion of the car.
Like which setting do I?
Oh, hold on just a second, I'll be right back. Okay, sorry about that. I have a student doing a lab at the same time. All right, so here we have distributive law, which is normal for mathematics, and also the distributive law can be used to demonstrate that the negative of a vector is just the negative of all the components of that vector. So if you have A with a negative in front of it, that negative distributes to all of the components because the components add together to be the full vector A. Here they talk about putting the Cartesian coordinate system into north, south, east, west, and up and down. And the standard for that is the I hat direction or X direction is east, J hat is, or the Y direction is north, and then K hat is altitude, or it's up away from the surface of the earth. That's standard in everything for the Cartesian coordinate system, just so you know. Let's see here. Two vectors A and B are equal. So if you subtract them from each other, they equal 0, and that's the standard. That is the standard definition of equality, actually. And there's a null vector that comes out of that is actually a 0 vector. So when you subtract two vectors and you get 0, it is a vector of 0. which is fine, I guess. What does that mean? Mathematically, it means a fair amount, I guess. In physics, what it means is that, you know, an equation is still an equation. So that whatever's on the right side has to be on the left side. If you have vectors on one side, then you're going to have vectors on the other side. So if the vectors are equal, that means their components are also equal. That's pretty straightforward, I think. For a resultant vector, when you're adding two vectors, you add the x components, that will equal the x component of the result, or the sum of those two vectors. Same with a subtraction, and so on. So those are all pretty straightforward things that aren't terribly difficult to understand. It's true for many vectors if you add them as well, instead of just two vectors. So here they do this. Here they do an example of adding some vectors. They've got the vector, let's see, what do they got? Vector R, D, and S, I guess is what they've got, R, D, and S. And they've actually got A, B, and C. Which ones are A, B, and C? I have no idea what vectors they're talking about there. But they give the lengths and the angles here, and that's good enough. So if I'm going to do this kind of a problem, I want to draw it out. And in the book and the examples, they don't necessarily draw them out all the time. I would always recommend you draw them out. So you have two or three vectors, A, B, and C, and you'll be tempted to draw these in such a way that is not very useful. Like, I have a lot of students who will do something like this, where they'll draw it, and so here's their coordinates. Oops. Here's their coordinate system, the y and the x direction. And they'll go ahead and draw them right one after the other. They'll do A is 10 meters and the angle alpha is 35 from the horizontal. So this is your 10-meter one. And then they'll do B is 7 meters and the angle is negative 110 from the horizontal, which is down like this. And so they'll try to draw this here to scale. And then they'll do C, which is 8, and it's gamma equals 30 degrees from the horizontal, so it's like this. And they're trying to figure out they're trying to figure out from this picture if they're correct. And like, well, first of all, it's difficult to draw vectors head to tail, head to tail, head to tail. And second of all, when we break them into components, it completely removes the need to do this. So why do it? If I'm going to draw a picture, I'm going to draw the three vectors from the origin because they're easier to draw that way. And if that means you need to have three coordinate systems, you know, you do one coordinate system, one graph here for one vector, one other one here for another vector. So that first vector looks like this. The second vector looks like this. And the third vector you draw separately on a separate coordinate system, and it looks like this. That's fine. If it means that you just draw them without coordinate systems, I would recommend drawing them all three like this. And why would you draw them at all? Because when you draw them like this, you make sure that you get the angles correct, and then you can actually do the, you can actually make your components on, you can draw in your components. Here's the X and Y component for this one. The X and Y component for this one has a short X and a negative Y component. This one has a fairly long X component and a fairly short Y component. Because that just kind of gives you an idea of what you should be getting, you know. In this, for example, in this one, these X and Y components should be pretty equal to each other. And so you should get something that looks like that, that kind of comes out that way. This one, you get a much shorter X and it's in the negative direction. And you get a longer Y that's also in the negative direction. So these two components should end up with a negative sign in front of them. Whether or not the math gives it to you that way, that's the way they should end up. So you should make sure that you end up with, this one should be a negative something I hat plus negative something Y hat. Or, sorry, negative something I hat plus, and then you can leave off the plus, negative something I hat minus something J hat. So you should end up with minus minus. This should end up with plus plus. And that's one of the biggest mistakes that is made when figuring out vectors, is that people will be doing the math and all the trigonometry, and in the end, they put in the answer with the wrong sign because maybe they wrote in the wrong angle or measured from the wrong axis, or you know, they did some goofy thing and they got a negative sign and they assumed that was really important. And if you do the math exactly correct, it is important. But if you don't do it exactly correct, and maybe like for this one that measures 110 degrees like this, maybe you just take this little angle down here, or you take this angle over here, that will not necessarily give you the same sign as it would have before. So you have to be careful if you're going to assume that all of your trigonometry is correct. What I do is I just create a triangle, pick an angle, and just remember that, you know, from my drawings which way these are supposed to be pointing. Because if you just pick a triangle, pick an angle, measure it from whatever axis you want to, and do the trigonometry will give you the right magnitude, if not necessarily the right direction. Here they do it with the actual correct angles, and so here they do it with the correct angles and the correct signs inside of the trigonometry, so it comes out the way it should in each case. 2 positives, 2 negatives, 2 positives. And then once they've calculated all of the components for each one of the vectors, then they add together the x components, they add together the y components, and they don't have any z components, they're good. And they get 2 new vectors, the resultant of both of these. And then the resulting vector from the addition of those 2 vectors is this number, 12.73 I hat, plus 3.15 j hat, good to go.
So that's pretty much like basically the same as our problem number 6 on our assignment, right?
Problem number 6. I don't know. I'd have to look at problem number 6. I don't remember what problem number 6 looks like.
Because I was having a little trouble figuring it out, but I was drawing the vectors head to tail, like you showed not to do, and you just showed to draw them all from the origin. So
Bringing everybody's scores up on this page, and they didn't want to do that. We're in chapter 2, right? So number 6.
I think it's 6.
Escaping a desert island, builds a raft, wind shifts, straight lines, boom, boom, boom. Yes, that's exactly how you do this.
Okay.
It's multiple vectors. Instead of just 2, it's like what, 5? 4, 1, 2, 3, 4 vectors, right? No, 5 vectors.
Yeah.
It's even more than that. Looks like it's a lot of vectors. 1, 2, 3, 4,
7.
5, 6. Man, this is just cruelty. Your teacher's a jerk. Why did he give you such a crazy problem for? The reason he gave you such a crazy problem is because it gives you good practice. That's why. What a nice teacher. Yeah, it is. But it's, I mean, this is not a terribly difficult problem, because by the end of this problem, you're going to get really used to creating these triangles and calculating, you know, these components and figuring out. You're going to get really good at it. And I would highly recommend that you use a method very much like they use here in the book. It's very straightforward. They do their x, their y for A. They do their x, their y for B. They do their x, their y for C. Then they add all the x's, add all the y's. And that's just one way to do it. My personal favorite way is a little bit different. I like to actually, on my page, I like to do the x components separately and then the y components separately. I might even break my page up into columns where I'm doing x stuff here and then y stuff here. One of those few times where I'll break my tradition of leaving the right side of the page open so that I can just have them right next to each other. And then at the end, I just calculate my total x here, my total y here, and I can just add straight down the column, you know.
Yeah. I also have another question though. Is the cosine component always the x or the I? And the sine is the j?
So let me show you an example where it might not be. So maybe your first vector is this way, right? And maybe your second vector is, maybe it's down this way or something like this, right? So maybe you walk this way for a while and then you walk this way for a while. And maybe the angle here is supposed to be 30 degrees, but the angle with this one, because the angles are usually given relative to the x-axis, but if they're not, Like in this one, it might say, 25 degrees west of north, right? Whatever. So if it says 25 degrees west of south, then this angle would be 25 degrees, right? That's west of south. And what I'll do is I'll write these two, I'll draw these two separately. So my first one is the 30-degree one here. And my second one is this 25-degree one down here, right? In this case, if I'm going to use the 25 degrees, my x component is going to point like this, right? And it's going to be opposite that angle. So this one, the x component of this, let's say this is vector b, b sub x will actually be equal to the length of b, whatever this distance is here, times the sine of 25, because it's opposite that angle. It depends on which angle you choose to use. Now, if you always use the angle between the x-axis and your vector, then it will always be the cosine. It just depends on which angle you use. And you can use the one that's between the x-axis. You just have to switch triangles. You have to use this triangle and use this angle, which of course is 90 minus 25, which is 65. So then you'd have a 65-degree angle. And then you can go ahead and say, this is my x component, which happens to be the same as this, right?
Yeah.
Excuse me. And then you can use that 65 and the cosine. So this one would be b cosine 65. It just happens that the sine of 65 is equal to the cosine of, the sine of 25 is equal to the cosine of 65, right? So, yeah, and that's a really good thing to bring up right now, because we will see many situations where we use that for one reason or another, just simple. Excuse me. So that takes us, that's kind of the basic algebra of vectors. Here they do another example where 4 dogs are pulling on a rope thing, and all these forces that they're pulling with add to 0. And that means they have to add to 0 in the x direction, and they have to add to 0 in the y direction. And apparently they have all the forces they know except for one. They don't know the force from the dog Doug, the dog. They know all the other ones. And so what they do is they set up an equation where this force from A in the x direction plus this force from B in the x direction plus this force from C in the x direction plus the force D in the x direction, which they just write as a variable, equals 0. And then they solve for that variable. And when you solve for that variable properly with the correct signs and all the correct, trigonometry in there, you can solve for that x component of Doug's pulling force. And then you can do the same thing in the y direction. And that's what they do here. They kind of do it in a funny way. They do they have A, B, C, and then they say, well, they're saying, well, if we add these all together and find the result, then Doug's should be negative of that result. Doug should have to pull back with negative the sum of all the other dogs pulling, because that's the only thing that will stop the other dogs from pulling. So they do it that way, but it's the same idea. And of course you can calculate the angle and the magnitude if you want to from that as well. So anyway, that's all. We call this just simple vector algebra, I suppose. It's more like vector. I wouldn't say it. I mean, that is vector algebra because you are solving for a variable, I suppose. But a lot of the stuff we just taught you is actually more just like vector arithmetic. That's fine. And they do lots of examples here of this kind of stuff, which is fine. We don't need to go through it forever. Another thing that's important to define is the unit vector, which we've done already, but right here they have that definition. A unit vector in general is a vector divided by its magnitude. So, a vector has length, whatever that length is. If you divide the vector by that length, you will always get a unit vector that points in the direction of the original vector. but is 1 unit long. It's only has a unit of 1, and so if you multiply by anything, it doesn't change the magnitude of anything, just gives it a direction. Is it still just the 3 of us? I haven't checked. There we go. Yep, just the 3 of us still. All right, so anyway, let's move on to products of vectors. And this should be new material for most of you. Is anybody in Calc 3 right now? No? Okay. So this will definitely be new material for all of you. So when you're multiplying vectors together, you run into issues, you run into problems, because how do you multiply directions together, for example? And it turns out that the answer is in the physics. When we have a reason to multiply 2 vectors together, we will get, the direction will be determined by the physics, essentially, what the physics is trying to accomplish. And in that case, we end up with 2 different kinds of vector multiplication for 2 different situations in physics. The first type of vector multiplication is what we call the scalar product. And the reason it's called the scalar product is because the result or the answer will be a scalar. It's also called the dot product because that's how we denote it. That's how we show what it is. And the dot product, when you're denoting it, looks like vector A dot vector B like this. And we actually say that. We don't say A times B when we look at this, we say A dot B. And that automatically tells people that we're multiplying vectors, A dot B. It's also called, see, the scalar product, the dot product, and it's also called a projection. And we talked about a projection already with the components of a vector, right? Doing components of a vector. Well, this is also a type of a projection where you're projecting one vector onto another, kind of. It's like multiply this. So the dot, what the dot product does is it takes one vector and projects it onto another vector and tells you how much of each vector is pointing in the direction of the other vector. Is kind of the way you could think of it, I suppose. And then, yeah. So that's kind of the idea, I suppose you could say. Anyway, oh, and the other thing it does is it multiplies those things together. It multiplies how much of each vector is pointing in the same direction as the other vector together, because it is a product. When we project onto an axis, we're projecting by multiplying by a vector by a unit vector, which means it only gets you how much of one vector is pointing in the direction of the other. But anyway, this is how we show it. And if you want to calculate it and you already know the magnitude of each of these vectors, you know the length of each of these vectors, and you know the angle between them, it's really simple. You just take the magnitudes times the cosine of the angle between them and you're done. No big deal. Scalar product gives you just a number. Won't give you any direction because there is no direction with the dot product. The dot product just gives you a number. That's all it gives you. The other way that you can do the dot product is using the components of the vector. So here they show an example of 2 vectors with an angle between them. They go ahead and use that form of the dot product and calculate that number right there. But the other way to do it, if you know the components of the vector, you can do this as well. The components of the vector, to use the components of the vector to calculate the dot product, what you do is you take the x component times the x component. Where do they? Oh, here they show it. You take the x component of the first vector and you multiply it by the x component of the second vector. And then you take the y component of the first vector and you multiply it by the y component of the second vector. And then you do that for the z components as well. And then you add those 3 numbers together. And then you're done. Should have drunk some water. My throat's all dry. Anyway, so either of those two methods will give you the same answer for the dot product. It doesn't matter which one. Here they're actually showing how this works. This works because the dot product is actually, it's actually kind of like a direct multiplication between these two things. But when you have I hat dot j hat, that goes to 0. Any two vectors that you multiply together that are 90 degrees to each other using the dot product. So if you do the dot product of two vectors that are 90 degrees to each other, you will get 0 because there's no overlapping direction that they point in. They're not pointing in the same direction at all, in other words. So what you have to do is, so what they do here is they actually do like the FOIL method, I guess, between these two vectors, and everything that has anything that's not I dot I or J dot J or K dot K, those all go to 0. So these two go to 0, this one goes to 0, these two go to 0, this one goes to 0, and all you're left with is the stuff on the diagonal here. The X components multiplied together plus the Y components multiplied together plus the Z components multiplied together. And that's the dot product in quick form. Here they show it in a much cleaner form. And so if you know the components of your vector, it makes it really easy too. Here I know the components of F1, I know the components of F2, and I know the components of F3. To find the dot product of these three vectors, if I, let's see, what are they trying to do here? Scalar product of these two vectors in the magnitude. They want to do the scalar product of F1 and F2. So the scale, if we're doing F1 dot F2, then all you do is you take 10 times negative 15, yeah, negative 150, negative 20 times, there's no J hat here, right? So there's a J hat here, but there's not a J hat here. So this would be negative 20.4 times 0. So that one just goes away. And then you have 2 times negative 6.2. So you end up with negative 150 minus 12.4. Negative 162.4 is your answer for F1 dot F2. And you can multiply, multiply F2 times F3 using the dot product. Get the scalar product between F2 and F3, a scalar product between F1 and F3. The scalar product you can only do once though. You can't do the scalar product F1 dot F2 dot F3. Because once you do it once, it's no longer a vector and you can no longer do that product, right? So, here they actually calculate the angle between these two vectors, which is this is a very useful formula. You can actually calculate the angle between two vectors in any dimensions, in 3 dimensions if you want, by taking the dot product of the two vectors, dividing it by the magnitudes of the two vectors multiplied together, and taking the cosine, taking the inverse cosine of that number. So they do that here and find the angle. So that's a very useful feature. So why would we do this? Well, turns out that there is there's something that we're going to be calculating later in this class called the work, which is the amount of energy that is required to apply a force and make something move some distance. And the reason that we use this particular multiplication is because the work is only interested in the force that's pointing in the direction of the displacement. It's only interested in part of the force that's actually pointing in the direction that the thing moves. If you apply a force in any other direction, you don't actually give it any energy in that direction if it doesn't move in that direction. So, so that's the primary place where we will use the dot product in this class, is calculating the work done. So the work is equal to the force dot with the displacement. And that's how we work it. So they give you the displacement and the force here, and then you're going to take the dot product between those and calculate the work done. You'll learn more about that, when we get to the chapter on energy. Now the next vector product is the cross product. The cross product multiplies two vectors together and gives you a vector output. You actually get a vector from a vector. It's also called the vector product. And we use, we use the X to denote this. And we usually say A cross B when we're talking about the cross product, A cross B. And the magnitude of A cross B is easy to calculate. It's just the magnitude of A times the magnitude of B times the sine of the angle between them. Looks very much like the dot product in that way, except it's a sine instead of a cosine. However, the direction of the vector that it results from this, if this vector A cross B is called C, for example, the vector is determined by using a little trick, you might say. And the reason that it's a trick that is done this is because the vector itself here is not actually a real vector in physics. So when you're using the cross product to do something in physics, what you're creating is a representation of the physical process that's going on that is standardized around the world. Everybody does it the same way so that we all know what we're talking about, but it doesn't necessarily represent something actually physical. Now that's debatable in some cases, but we can talk about that later, I suppose. But what do I mean by this? So one of the ways that we use, one of the most common ways that we use the cross product is in calculating torque. Torque is kind of, you can think of torque as twisting force, I suppose. It's not really a great definition, but it's, something close. The torque is caused by a force that is pushing on an object, but not pushing on an object in a direction that passes through the center of mass of the object. So if you're pushing off center on an object, for example, if you push, let's draw a picture here really quick. Let's say we're on a sheet of ice, a pond or something like this, right? And we have this big boulder in the center of this sheet of ice that we want to get off the ice. We want to push it off the ice. And this is the center of mass of the object. In other words, this is where effectively gravity pulls down or something like this. You could balance this rock on this point, for example. That's the center of mass, right? So if that's the center of mass looking from above on this rock, and I push this rock right in this direction, this rock will go straight off in this direction and not do anything else. However, if I push here, because there's a little bit of friction here on this part of the rock, as I start to push here, the little bit of friction that pushes back over here has nothing to oppose it back here. And so this rock is going to start to rotate this way. The friction that's here has something to oppose it. But the friction over here and the friction here and the friction here, nothing to oppose those frictions. So it's going to start to rotate, right? And that's what I mean by a twisting force or a rotating force. Forces that cause rotation are torques, but does that mean that, well, are associated with torques. But that doesn't mean that this force is a torque, because this force is a force, not a torque. So how do we associate it with something we call a torque? Well, when it comes to torque and rotating things, there are two things that matter. There's the force applied that matters. If you have a bigger force, you're going to get more torque. But also the distance between where that force is and where the point at which it's rotating around, or any old point, really, it doesn't matter as long as you pick a point and stick with it. But the distance between those things is going to affect the torque. Think of a door. When you're opening a door, you open it from the handle and it's pretty easy to open. But when you're trying to open it for somebody else and you open it at the hinge, it's much harder to push, because the distance from the hinge makes a difference in how much torque you are applying or have to apply. So that's where we use this kind of thing. So how do we get from a force to a torque? Well, we use the right-hand rule. Because force and distance are both important in this, then we draw a vector from the center of mass, or from some point that we choose, it doesn't have to be the center of mass, out to the place where the force vector is acting. We call that the distance vector, d. And then the torque is equal to F cross, actually it's the other way around. It's D cross F. And it matters. With the cross product, the order matters. If you take D cross F and you find the vector for D cross F, you will actually get negative F cross D. F cross D will give you the exact opposite vector. So D cross F is a cross product that we use to determine this. And of course, we already know, because we just learned it, that we can calculate the length of D using this. You just take the original two vectors, their lengths, multiply them together, take the sine of the angle between them, you're good, and you're done. The sine of the angle between this D vector and this force vector is like this angle right here. So you can measure that, or if they tell you that, you're good. Whatever, and then you put that in right here in this equation. You put the length of this one, F, in here, and you put the length of D in there, and you're good. And you've got the length of the resulting vector. You just don't know what direction it's pointing. But what you do know is that we use this thing called the right-hand rule. And the right-hand rule says that you stick your hand in the direction of the first vector in the cross product, like a karate chop. Let's see if they do it here for us. They should somewhere. Not really. Okay. Torque, right hand rule. Torque, right hand rule. Okay. So here is a force that's causing this disk to rotate. It's not a rock, but it's a force in a disk. Here's the distance from the center of the disk out to that force. We're going to put our hand in the direction of the R. That's the first vector. And then we're going to turn our fingers in the direction of the F, kind of turn the four fingers in the direction of the F. And then our thumb will point in the direction of the torque, which is up like this. So if I drew my hand, I don't know if you can see my, draw a hand. So my hand is pointing this way. Here's my hand. And here's my thumb, like this. I put my hand in the direction of R, and then I turn my fingers in the direction of this, and my thumb is still pointing up like this. Kind of like I'm hitching a ride, but my fingers are now pointing this direction, which is the direction of the force. My thumb is now pointing up, and that's the direction of my actual torque. When you do the right-hand rule, the resulting vector always is 90 degrees to the original two vectors. The original two vectors are always going to form a plane or define a plane somewhere, and your torque vector will come out of that plane, or your resulting vector will come out of that plane one way or the other.
This one because there's
No, don't worry about that. Okay. So that is the idea of the cross product and how you find its direction. So let's do an example of that really quick, because this can get really confusing. Yeah. Clear all drawings. Okay, so let's do an example of the cross. Oh, yeah, here's an example. No, that's not it. Here's an example of the cross product. Here we have a wrench that we're turning a bolt with, and we have this distance from the bolt to where our hand is applying the force, and here's the force. And so which direction is so to get the magnitude of this vector cross product, you just take the length of this times the length of this times the angle between them, the sine of the angle between them, and you've got it. But what's the direction of this one? Who can tell me what direction the torque is for A? So you make a blade out of your hand like a karate chop, stick it in the direction of the R, turn your fingers in the direction of the F. Is this one coming out of the screen or into the screen? Out of the screen. Out of the screen. Okay, good. So how about this other one in B? Which one is it? Out of the screen or into the screen? Karate chop it, put your hand in the direction of R, turn down in the direction of F, into the screen, right? So the torque for tightening and the torque for loosening are different. They're opposites, right? This one is the torque for loosening. This one, the wrench is going to go around this way because the force is pushing it this way. This one is the one for tightening. So distance differences. Now, the last thing I'm going to teach you really quick is how to calculate the torque if you know the components of the vector. And the math of it is, you know, the actual vector math of this is fairly complex. But what it comes down to is a formula that you can actually write down. It's not a simple formula. It's kind of messy. But if you have two vectors that are three-dimensional, then the cross product is calculated by using this formula. You take the y component of A times the b component, the z component of B, subtract, and these are all magnitudes, not actual vectors. They just tell you the length of each of the vectors, minus the z component of A times the y component of B, and all of that gives you a number, and you multiply that by I hat. That's your I hat direction. And then there's two other formulas for this. And you can actually calculate any two vector the cross product between any two vectors using this formula if you know the components of each vector. It doesn't matter if you're in 2 dimensions or 3 dimensions. You're going to end up in 3 dimensions anyway because the cross product will always create that new dimension if you're only in 2 dimensions. But this right here is the formula for calculating that.
So those up there, those are the magnitudes of each. So like if it gives you an I value and a j value.
Yeah. So if your vector is 4 I hat minus 3 j hat, for example, then the 3 j hat for A would be the y component of A, and you'd put the 3 right there, not the j. You'd just put the 3 right there.
Yeah.
So it's the component of it's the magnitude of each component is what these are.
Okay.
And then you put these unit vectors on them, and that gives you the vector that you're looking for. And that's very useful when your cross product creates a vector off in some wonky direction in space. So, all right, that's enough for today. Go ahead and get working on the rest of the homework, and then we'll come back on Friday. Let's see, what did I put the due date as? I don't remember. Yeah. Oh, so we need to change that again, right?
Yeah. You changed it over the weekend, I think.
Yeah. We'll change this until like Saturday or something.
Oh, I put in an extension. Will it still affect?
No, it'll change that. Let's see, due the 12th. All right. And I have to save it. I always forget to save it.
So is that right-hand rule related to how if you have a current going this way, the magnetic field
Yep.
will go this way?
Yep. It is. All right. Have a good day.
Yeah, you too.
Is there a lab tomorrow?
Yes, we will have lab tomorrow.
You can leave the stuff here for me to do lab if you don't want to come in at 11. Or I think 11.
I'll be here at 11 anyway.
Oh.
So it doesn't matter.
Okay. Thank you.
Yeah, okay, this is going to Darwin.
This one. I really needed that. Okay. How was your labor day? It was okay.
You have to go to workforce school. That's nice.
Where are you working?
They started there.
They closed for labor day or hang on?
Yeah, we had close. That was nice.
A real day off. With school and work. Monday. We do. I played a board.
So it's fun.
I love it. I collect board games. I'm up to about 60 of them now. I'm wanting to try out a new one. Play as your favorite Disney villain. And you try and make your animated fate watch. There's well, everyone else tries to give you the fairy tale. It's a fun one. I've played as Maleficent and Ch2a, but there are 4 other characters and a bunch of expansions.
Oh.
So, I do not on my list. I've heard that it's quite good.
Are you a gamer too?
Yeah.
You done Exploding Kittens. That's a fun one.
Made by the same people.
He also did Throw Burrito, which I heard is fun.
Oh, yeah. I haven't.
Do you play games a lot?
Card game?
Yeah, card games, board games. No,
I
really.
mean, card game a little bit.
Yeah.
So,
I didn't even know that there was like a gaming community of board games and card games until Packer took it up. I thought gaming just meant video gaming, which I'm also not into. I grew up with all the video games. I had a friend, I still have a friend, actually, different friend, but I had a friend that had the original console Pong game when I was a kid in his grandparents' restaurant. And the original Pong game, you know what Pong is? So the original Pong game was a table that you sat at. The screen was in the tabletop. You put your hands under the edge of the table and there was a ball that you rolled around, and that's what moved your paddle back and forth, and you played against somebody on the other side of the table. And we have a friend here in North Platte that actually has one of those, right? Brian?
He has Pong. He has Asteroids. But I think that's the only sit down. And
No, isn't his Pong? Asteroids is his table game? Oh,
Yeah.
I thought he had Pong. But anyway, I had a friend that had Pong. And that was the first real, like, video game that was made for, like, putting in it was really the first video game made for any reason. And then I, of course, grew up in the video game arcade era. So there were arcades everywhere. Never was good at those things. Grew up with all the great the old consoles like the Atari 2600 and the ColecoVision and the what was the other one? Don't remember. There were 3 that were the first ones, and then Nintendo came out and Sega and everything else after that. Never got good at it, never even liked it. Okay. Today, I don't remember what we're doing. Does anybody remember what I said we were doing? Oh, we're going to start learning about the engineering process. Isn't that right?
Sounds right.
Yeah, that sounds right. Oh, crap. I've been recording my